Pluto made them come from the start. It was like it was never really a segment of the nearby planet gatherings. Pluto's planetary moderate framework crosses that of another planet, and that is no kind of direct for a planet. Pluto, the bewildering, more modest individual planet at the edge of our planetary gathering, is causing a commotion in the cosmic neighborhood. Recent reports suggest an oncoming crash with Neptune, lighting stresses among analysts and space lovers alike. Esteemed experts, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about the expected consequences of this heavenly clash. Anyway, how did Pluto regard itself as on a compressed course with its faraway neighbor? Also, what might this bombastic accident possibly mean for our world on Earth? Join us as we dig into the alarming situation developing between Pluto and Neptune. Pluto, once seen as an obvious planet, was later renamed as a dwarf planet because of its unusual orbit. Nevertheless, this change doesn't prevent it from continuing to entrance and attract the astronomical community. Later conjectures from renowned analysts, including Neil deGrasse Tyson and Michio Kaku, have highlighted an agitating closeness between Pluto's orbit and that of Neptune. These experts are cautioning about a possible impact between the two planets, representing a critical risk to Earth. The idiosyncrasy of Pluto's orbit around the Sun lies in its unique characteristics within our nearby planet group. Its orbit ranges in 248.50 years, and Pluto has not finished a full revolution. What adds to its appeal is the incredibly curved nature of its orbit, a departure from the almost round orbits of the major planets. Also, Pluto's orbit is marked by a 17 degrees tilt to the ecliptic plane, making its path more extreme as opposed to other planets. This combination of tilt and eccentricity presents layers of complexity to Pluto's orbital design. A surprising portion of Pluto's orbit lies in its intersection point with Neptune's path. For approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their respective positions in the nearby planet group. This prompts the question, why hasn't an impact between Pluto and Neptune occurred? The explanation lies in the gravitational impacts exerted by different planets. The appraisal of Pluto's orbit began not long after its discovery, presenting a surprising direction for cosmologists. As opposed to most planets, whose orbits align generally near the ecliptic plane, Pluto's unique features include a steep tilt and an eccentric shape. The mystery expanded with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amidst these complexities serves as proof of the intricacies inherent in space mechanics. The three-body problem in space involves understanding the motion and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. It is akin to predicting their paths based on initial positions and mutual gravitational impacts. For Pluto's situation, this issue explains the complex interaction between its orbit, Neptune's orbit, and the gravitational pull of the Sun. Terms like lopsided libration, scope libration, and the VZK oscillation contribute to unraveling this celestial conundrum. Astrophysicists state that libration, responsible for maintaining planets in their orbits, plays a crucial role when it comes to Pluto and Neptune. This term means that when Pluto crosses Neptune's orbit, it is arranged something like 90 degrees away from Neptune, essentially preventing potential collisions. Scope libration, referring to the vertical movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is situated entirely above their orbital plane, providing an additional layer of protection against collisions. A critical factor in understanding celestial movement, VZK oscillation, named after three scientists, von Zippel, Lilly, and Kai, who studied the gravitational interactions between three space objects like Pluto, Neptune, and the Sun, helps explain why Pluto's orbit around the Sun seems irregular but remains stable over time. Despite the apparent randomness in space, underlying patterns and rules keep everything in order. These factors generally stabilize Pluto's orbit, preventing crashes with Neptune or deviations from its path. The three-body problem helps us understand how the gravitational forces of these space objects affect their paths. Examining this adds to our understanding of Pluto, our nearby planet group, and distant celestial bodies. Numerical simulations in the late 1980s revealed that despite its turbulent properties, Pluto's orbit is indeed stable, with minor initial deviations leading to significant differences over millennia. However, Pluto's extraordinary orbit maintains stability over unimaginably long timescales, keeping chaos at bay. Later virtual simulations have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun-Neptune's orbital resonance, where it completes 3 orbits for every 2 of Pluto, contributes to stability. Jupiter's gravity also plays a significant role, and Saturn has a smaller influence. Together, these forces ensure Pluto's safe and stable motion through space for billions of years. These peculiarities are crucial for maintaining order and consistency in the movements of objects in the universe. Without these elements, the nearby planet group would be a place of greater disorder and unpredictability, potentially leading to collisions or ejections from stable orbits, affecting other celestial bodies. Understanding Pluto's orbit is important, especially in discussions about a possible collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of our planetary system. Pluto's case highlights how seemingly unstable orbits can reach equilibrium through the complex interaction of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our position in the universe. Exploring the depths of space often uncovers the whimsical nature of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The concept of orbital chaos, representing the delicate dependence of a celestial body's path on its initial conditions, is strikingly demonstrated in Pluto's case. Indeed, even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Numerical simulations have been instrumental in helping scientists understand how Pluto moves in space. These simulations use complex mathematical models to replicate the gravitational interactions between Pluto and other celestial bodies, such as Neptune. By making small changes in the simulations, space specialists can see how minor adjustments can significantly affect Pluto's trajectory. In the late 1980s, these simulations uncovered an interesting aspect of Pluto's orbit. Despite factors like AIML and scope libration that contribute to its stability, Pluto's orbit can still exhibit unpredictability. Even a small initial difference in Pluto's position or speed can lead to significant changes in its path over many years. Nevertheless, despite this inherent chaos, Pluto's orbit remains stable over an extraordinarily long time frame, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized pattern. Predicting the long-term behavior of celestial bodies, particularly those with eccentric orbits like Pluto, is incredibly challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Numerical simulations help us understand and predict the future paths of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily depend on accurate initial conditions and simulate complex interactions, and even a small error can lead to significantly different results, making precise predictions difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our continued limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the planetary system. It shows how each planet's presence and position can affect the stability and path of other bodies within the system. Despite these complex forces, prominent astrophysicists are now expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such a collision, which seems improbable given these unusual factors, is now a subject of concern. Neil deGrasse Tyson, a prominent astrophysicist known for popularizing space science, offers a unique perspective on the mysteries of our planetary system, particularly with respect to Pluto. Well known for renaming Pluto as a dwarf planet rather than a true planet, Tyson shares insightful thoughts on how our understanding of celestial mechanics is continually evolving. He views Pluto's renaming not as a downgrade, but as a significant adjustment in line with our growing understanding of the various objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexity of orbits like Pluto's as a sign of how much more there is to discover in space. Tyson believes that the challenge of these questions makes astronomy so fascinating. Moreover, Tyson is aware of how space-related events and discoveries shape public interest in space science. He believes that events like Pluto's renaming and its unusual orbit present opportunities to captivate the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes whimsical aspects of space mechanics, he opens a window for the general public to wonder about the marvels and mysteries of the universe. Working alongside other analysts, Tyson is actively warning the public about the possible risks of Pluto's unusual orbit. After studying Pluto extensively, he has raised concerns that the three-body problem could present a real danger, suggesting that a collision with Neptune is long overdue. Furthermore, he emphasizes that such a collision could disrupt the balance of the universe and lead to catastrophic outcomes extending to Earth. A collision between Pluto and Neptune would be a remarkable and devastating event in our planetary system. This impact would release a tremendous amount of energy, potentially breaking Pluto apart due to its smaller size and cold composition. Debris from the impact could disperse across the planetary system, posing potential threats to other planets and their moons. For Neptune, such an impact could even alter its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory and physics, offers a new perspective on this situation. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide valuable insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can provide valuable lessons for future space missions. This knowledge can support exploring the nearby planet group more effectively, predicting potential hazards, and planning missions to the outer regions of our planetary system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, offering a roadmap for approaching and understanding distant worlds. When discussing the physics of planets, Kaku often highlights the deep connection between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, like the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to understand these principles at the most basic level. He suggests that considering the intricacies of celestial mechanics, such as Pluto's orbit, could offer insights into the essential laws of the universe. Like Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in cosmology, offering a unique observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces in the universe. An impact of such magnitude in the planetary system could generate extreme conditions of energy and gravity, providing insights into the behavior of fundamental particles and forces under extreme circumstances. The potential collision between Pluto and Neptune, while seeming improbable, continues to captivate both astronomers and the public. Experts like Neil deGrasse Tyson and Michio Kaku are especially keen on exploring the possible implications of such an event. They emphasize that the dynamics of the planetary system are far more complex than a simple collision scenario. Tyson, known for his educational outreach in astrophysics, often points out that the evolving nature of celestial mechanics presents numerous possibilities that defy our intuitive understanding of the universe. The delicate balance between celestial bodies, especially when influenced by factors like gravitational resonance and the three-body problem, suggests that the future of Pluto's orbit might hold surprises even for the most seasoned scientists. For Kaku, the study of Pluto's orbit provides more than just a window into our solar system. It offers a path forward for our understanding of the cosmos at a fundamental level. The intricate dance of gravitational forces within our planetary system is closely tied to theories of string theory and quantum mechanics. A collision, though unlikely, could serve as a cosmic experiment, shedding light on the behavior of matter and energy under extreme conditions. Observing such an event would not only provide insights into planetary mechanics, but also deepen our understanding of the very forces that govern the universe. The gravitational interactions between Pluto and Neptune have been shaped by the larger planets like Jupiter and Saturn, whose gravitational pulls help maintain the stability of Pluto's orbit. The influence of these giants ensures that even if Pluto and Neptune cross paths, their orbits remain in sync in a way that avoids disaster. This finely tuned balance exemplifies the complexity of the solar system and the forces that keep it intact. It also highlights the limitations of our ability to predict the future of these celestial bodies with absolute certainty. The ongoing study of Pluto's orbit continues to challenge conventional understanding of celestial dynamics. While the likelihood of a collision with Neptune remains low, it's crucial to note the ongoing evolution of astronomical methods and technologies, which continually refine our predictions. By improving models that simulate orbital mechanics, scientists are increasingly able to account for variables that may have been previously overlooked. These advancements in technology enable a clearer view of how celestial bodies, including Pluto and Neptune, interact over millions of years, offering new insights into the long-term behavior of our solar system. Moreover, the scientific community has emphasized the importance of collaboration across different fields of astrophysics and theoretical physics. While astronomers focus on planetary orbits and gravitational forces, physicists like Kaku extend these concepts into areas such as energy, mass, and the fundamental structure of the universe. The intersection of these disciplines could ultimately reveal deeper connections between the dynamics of planetary systems and the laws of physics that govern the universe. As our tools and understanding advance, there is growing excitement about the potential for future space exploration missions. These missions could provide direct observations of outer solar system phenomena, including Pluto's eccentric orbit. Such explorations would not only enhance our knowledge of planetary dynamics but also expand our broader understanding of the cosmos.